Hi, 7th grade. Welcome to lesson 4.8, Analyze Equivalent Expressions. By the end of the lesson, I want you to be able to say, I can use an equivalent expression to find new information. Let's solve and discuss it. How many toothpicks make a triangle? 2 triangles? Write an expression that represents the number of toothpicks needed to make X triangles that appear side by side in a single row as shown. Explain your reasoning. Okay, so let's make a table. This is going to be X. That's the number of triangles. And this is going to be Y. That's the toothpicks. So I'm going to put toothpicks and I'm going to put a triangle. So what I want you guys to do is fill out for 1, 2, 3, 4, and 5 triangles. I think we'll get the point by then. Pause the video and share your findings. Okay, hopefully you found to make 1 triangle, we only need 3 toothpicks. Then to make the second triangle, we only have to add on 2 more. So that's 5, then 7, 9, and 11. I hope someone found the pattern. What is happening each time? We're increasing by 2. That is our slope. That is our rate of change. So they're asking for us to write an equation. And that equation, or an expression, that expression would be 2x. But is it always 2x? 1 times 2 is not 3. So we need to add 1. So let's check, okay? So we have our expression 2 times your number of triangles plus 1. That does equal 3. Let's try another one. 2 times 2 triangles plus 1, that equals 5. 2 times 2 is 4, plus 1 is 5. We'll try one more. 2, times, let's go down to the bottom. 5 triangles, plus 1. 2 times 5 is 10, plus 1 is 11, and it checks out. So our expression works. Focus on math practices. Can there be more than one expression that represents the total number of toothpicks needed to make X triangles in the arrangement shown? Explain. Instead of adding 1, we could possibly multiply by 2 or by 3, maybe 4, and subtract some. So yes, there are multiple ways to write this. We could write it as, we could even do practice R, 2 times x plus 1/2. That would be factoring. We could break it up as x plus 1. That would be like before it was combining like terms. All right, example number 1. A new box of pasta claims that it contains 25% more than the usual box. What expression shows the amount of pasta P in the new box? Well, we have our old box, that's P, and we want to add, that's 1P, add the 25%. Remember, 25%, we divide by 100. Dividing that by 100 will give me 0.25. But it's not just 0.25, like what, 0.25 what, noodles? It's 0.25% more than the original box. So we'd have to multiply the original box by 0.25. But these are like terms. We can add them to get 1.25p. So 25% more than 100 is the same as 125, because you could just take that 25%, add it to the 100% and get 125%. Let's try it. Joe is buying gift cards that are on sale for 15% off. So that means we're going to subtract. He uses C minus 0.15C to determine the sale price of the gift cards. What is an equivalent expression that Joe could also use to determine the sale price of the gift card? Well, if that's C, that's like 1C minus 0.15C. These are like terms. So I combine them. 1C minus 0.15C is equal to 0.85C. And that's what's going to go in this little box, 0.85. That's when we take off the 0.15. Convince me. How do you know if an expression is describing a percent increase or a percent decrease? Well, maybe to give you a hint, the percent increase gave us 125%, and the percent decrease gave us 85%. Do we see a pattern? Is there something that's maybe more than something or less than something? We're always starting with 1 or 100. So a percent increase is bigger than 100, and a percent decrease is less than 100. So if I said 67%, we would know it was a decrease. If I said 115%, you would know it's an increase just by telling if it's bigger or smaller than 100%. Example number 2. Analyze equivalent expressions. Some middle school students will use 1-foot tiles to create a frame around a large square mural painting with side lengths s feet. 3 students each wrote an expression to determine the number of tiles needed. Are these expressions equivalent? Explain. So this expression has 4 on the outside and s plus 1 on the inside. When I see a number on the outside, I know that I have to use the distributive property. So I'm going to distribute in the 4. 4 times s gives me 4s, and 4 times 1 gives me 4. The next student, combining like terms, I've got an s, 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 s. That's 4 total s's. So that's 4s plus 4. The last student, I see again my distributive property. So I distribute in the 2, I leave the 2s, that first one. Then 2 times s is 2s. 2 times 2 is 4. Combine like terms, that's 4s plus 4. Even though they were originally written different, simplifying the expressions tells me that they are all the same. So the 3 expressions are equivalent because they each represent the number of tiles needed for the frame around the painting. Example 3. Interpret equivalent expressions. A table with a rectangular top has been extended with a table leaf shown. So the original table is blue. The leaf, the thing that you add to make the table longer, is green. It says multiply 3.5 times 6.5 plus x to write an equivalent expression for the total area of the extended table. What does each term of the equivalent expression tell you about the table? Well, 3.5, that's our length. And 6.5, that's our width of the original. And then when you have 6.5 plus x, that's the width when they have the table leaf added. So multiplying in, distributing in, 3.5 times 6.5 gives me 22.75. That's what we already know, 3.5 times 6.5. That's the area of the original table, the blue part. Then 3.5 times x, that's going to tell me the area of the green part, the new table leaf added on. When we add those together, that's when we'll find the area of the entire thing. We can't find the actual area of the entire thing until we know what x is, what the width of the table leaf itself is. That's why we use the variable, because we're not sure yet. The total area in square feet of a rectangular stage that has been widened by x feet is represented by 1,900 plus 76x. Use the distributive property to factor the expression. What does each factor in the equivalent expression tell you about the stage? Well, I know that the length is going to be this part. That's going to be what we divide out. That's going to be our GCF. And the width is going to be something plus x. So that tells me I'm going to try my GCF of 76 because I want that x to be by itself. So I take my calculator and I do 1900 divided by 76, and that equals 25. 76 divided by 76 cancels out. Please don't forget that last step of getting 76 on the outside. So when I factor that out, that 76 is my length. We already have the x accounted for, so the width of the original stage must be 25. So the length equals 76 feet, and the width equals 25 feet. Cool beans. Okay, 7th grade, let's say it. I can use an equivalent expression to find new information. Have a super great day.